Welcome back. In this series of lessons, we're going to be looking at multiple reactions and how we can quantify the production of desired products compared to waste materials that come from side reactions. So frequently we have these desirable reactions, but along the way other products might be made. In the case shown here, we have a desired reaction where we are using ethane to produce ethylene and hydrogen. Unfortunately, once that ethylene is created, it may react with some of the ethane to create propane and methane. So we want to be able to describe how much of the desired product is formed, in this case the C2H4, compared to how much of the undesired products, methane and C3H6. Two ways of doing this are yield and selectivity. Yield is going to be the ratio of the moles of desired product formed to the moles of the desired product that would form in the best case scenario. Now, the best case scenario is when there are no side reactions and 100% of the limiting reactant is consumed. This will always give a value between 0 and 1. Selectivity is going to be the ratio of the moles of the desired product formed to the moles of any undesired product form. Now, we're going to need to specify which of those undesired products we mean. It can be any positive value. So if a number is less than 1, you are not producing very much of your desired product at all. You're producing mostly waste materials. But as the selectivity goes to infinity, you are producing virtually all desired product and no waste materials. So let's look at an example. Now, in order to do this, we want to begin talking about extent of reactions with multiple reactions. Now, extent of reaction is going to be specific to a particular reaction. So therefore, there will be a different one for each reaction. So if there are J reactions, there will be J values of squiggle, okay, 1 per reaction. And there are stoichiometric coefficients for each of our materials for each of those reactions. So instead of using just the number of moles at the exit equals the number of moles at the inlet plus beta, remember that's the signed value of the stoichiometric coefficient times squiggle, the extent of reaction, we're going to have the sum of all the betas times squiggles for each of the reactions. So let's just do that for each of our components in this reaction system that we've talked about here. So I have several different components, and let's look at each one of those in turn. So for C2H6, if this is reaction 1, 2, and 3, C2H6 is going to be, at the end, is going to have the initial number of moles, okay? It's consumed, so minus squiggle for reaction 1. It also, however, figures in reactions 2 and 3. So minus squiggle for reaction 2, minus squiggle for reaction 3. It's a reactant in all cases, so negative, and it is got a coefficient of 1 in all cases, so therefore just minus squiggle 1, minus squiggle 2, minus squiggle 3. Now I can do this for each of my compounds. If I do C2H4, the number of moles at the end is the number of moles at the beginning, plus squiggle 1. It is formed in reaction 1. It is not involved in reaction 2, and in reaction 3, it is a reactant, so minus squiggle 3. H2 is in the amount initially in there. It is formed in reaction 1. It is consumed in reaction 2. I also have CH4 and C3H6. For CH4 is not involved in reaction 1, but in reaction 2, 2 moles are formed, so plus 2 squiggle 2, and 1 mole is formed in reaction 3, plus squiggle 3. And for C3H6, start with the initial amount, nothing from reaction 1, nothing from reaction 2, 1 mole from reaction 3. If I had any inerts, then the number of moles at the end will equal the number of moles at the end, because the stoichiometric coefficient for all terms is going to be 0. Another key thing to talk about is overall and single pass conversion. Now again, this can be the same as it was for a single reaction. For the overall conversion, it's going to be the moles of the fresh feed minus the moles in the product and purge streams. Okay, so what comes out divided by the moles of A in the fresh feed. Now A could be any of those reactants. For single pass conversion, you would do the same thing, but looking only at the inlet and the exit to the reactor. The key thing with looking at overall and single pass conversion is that typically one looks at a key reactant that makes the desired product, as opposed to anything extra. Maybe frequently, like oxygen could go to combustion, could go to making a desired product. So we would not typically do the conversion of oxygen, we typically do it of the other material. In this first example, we have the reaction scheme CH4 plus O2 makes HCHO plus H2O, which is the desired product, HCHO, or CH4 plus 2 oxygens makes CO2 and 2H2O. This is a combustion reaction that is not desired. Now, the fractional conversion of CH4 is 95%, fractional yield is of HCHO is 90%. We are going to want to know what is the molar composition of the product stream and what is the selectivity of HCHO compared to CO2. Now I realize that I left one item off of this drawing here, and that is what we have coming in. So my feed in this case is an equal molar mixture of CH4 and O2, and I will use this 100 moles as my mixture. So at the end, I'm going to have CH4, I'm going to have some O2 left, I'm going to make some HCHO, I'm going to make some CO2, and I'm going to make some H2O. All right, so with this as my given feed scheme and these two pieces of information given, I want to know what my molar composition of the product will be and what's the selectivity of the desired product to the undesired product, CO2. Now, I have two process specs. So my first process spec is that the fractional conversion of CH4 is 95%. I can use this with the definition of fractional conversion. 0.95 equals the amount of CH4 that reacts divided by the amount of CH4 that's fed. In this case, 50 moles. And based on this, X is 47.5 moles of CH4 that react. This means that the CH4 that exits is going to be the amount that came in minus the amount that reacts, will be 2.5 moles of CH4 that exit the system. Okay, what about the other process spec? Well, this one I also have enough information to use initially. This one says that the number of moles of HCHO formed compared to the number of moles that could have been formed if the initial feed of CH4 all produced CO2. Now, either one, it could be CH4 or O2 because this is a stoichiometric feed. Otherwise, you would always choose the limiting reactant. So this is 50 moles of CH4. And based on reaction 1, if this all goes to HCHO, 1 mole of HCHO comes from 1 mole of CH4 using the stoichiometric ratios. And so therefore I have 50 moles of HCHO that could be made in the best case scenario, and therefore 45 moles of HCHO are actually formed. Now I've used the process specs here because I was able to. I typically write the process specs into equation form. If I can solve them, I go ahead and do it now. Otherwise, I at least have them written as an equation before I go on to the next steps. I consider that to be part of the drawing phase. So I've defined my basis, I have a drawing. My next step would be to write a material balance table, a degree of freedom table, and solve this. But I have two ways of doing this. I can do this using a molecule balance, or I can do this using an atom balance. We're going to first do this using a molecule balance, and then we'll follow it up by doing the same problem with an atom balance. So using a molecule balance, what I'm going to do is I look at my feed, and I look at my product, and I list all the molecules. And I can list the total. I have in the feed 50 and 50 and nothing of the others, leaving me at the total of 100, and all of these are in moles. And in my product, I've already determined that I have 2.5 of CH4, I have 45 of HCHO, and then I have undetermined amounts of these others. So let's label these A, B, and C. Now, in this particular case, if you look at each of the reactions, they are both equimolar. 2 moles makes 2 moles, 3 moles makes 3 moles. So therefore, the total is going to add up to 100. That can save me a little bit of effort solving problems later if I wish. Now this is my material table. What's my degrees of freedom? Well, degrees of freedom, I'm going to count my number of reactions and my number of variables. In this case, I have 2 reactions and I have 3 variables. Then I look for equations that I might write. I have a material balance for each of my components. So 1, 2, 3, 4, 5. Sum of x's, I have 1 actually, and process specs, I have none because I've already used them. Okay. If I had not used them, I would have still had CH4 and HCHO in the product unknown, and those 2 process specs would have added to my count of equations. So if I do this, then my degrees of freedom is going to be 5 minus 6, so -1. This means the problem is somewhat overspecified, but that's okay. Go ahead and solve it anyway. At least I know that if it's 0 or negative, I should go ahead and solve the problem. If it's positive, I should keep looking for information or go as far as I can and then figure out what more information I need. So what are my equations? Well, use the equation Ni equals Ni naught plus beta squiggle for each of the J equations, the sum of those. So in this particular case, if this is equations 1 and 2, I know that 2.5 equals 50 plus squiggle, let's make that a minus, minus squiggle 1 minus squiggle 2. For O2, I have A is equal to 50 minus squiggle 1 minus 2 squiggle 2's. HCHO, that's 45 equals 0 plus squiggle 1. CO2, B equals 0 plus squiggle 2. And C equals 0 plus squiggle 1 plus 2 squiggle 2's. So my equations are found using this. So these are my material balance equations. Okay? This is a much easier way than actually kind of going through all the games and writing out the reaction. This is the same as what I would get if I did a proper material balance, N equals out plus generation. And this is kind of a shortcut to doing that. Now, I'm going to solve these. This one tells me what squiggle 1 is. If I plug that in here, I can solve for squiggle 2, which means that B is equal to squiggle 2 is 2.5. And now I know squiggle 1 and squiggle 2, so I can solve for A. Okay, so I'm able to completely solve these equations. Now let's try this again using atom balances. So it's the same problem. I have the same information. My material balance table, in fact, will be the same. Okay, what's going to change is my degree of freedom table. On the degree of freedom, I don't have to worry about numbers of reactions because atoms don't react away. So therefore, I only have the number of variables, which is 3, the number of material balances. Now this time, instead of counting molecules, I count atoms. And I have C's, H's, and O's. So I have 3. My sum of X, well, I can add those up to get 100. So I have one of those. Process specs, I have 0, and again, I end up with -1. So this is slightly over-specified. Let's go ahead and solve it anyway, and then just you go back and check and make sure that the sum of X equation, that all of these really do add up to 100 to verify that your answer is good. So now then, the key thing that's different here is how do you write those material balances? On an atom balance, it's always input equals output. I don't use the squiggles. So I write one of these for each of my atoms. So I have carbons, hydrogens, and oxygens. In this case, carbon is going to be here, here, and here. So coming in, I have 50 moles of carbon atoms. Coming out, I have 2.5 with the CH4. I have 45 with the HCHO, and I have B with the CO2. So I could solve this for B, and in fact, I'm going to get the same answers as I did a moment ago, where B is going to equal 2.5. Okay, what about the H's? Well, there are 4 of them in the CH4, so 4 times 50. Let me write it that way, a little easier to read. So 4 times 2.5 come out with the methane. 2 times 45 come out with the HCHO. And 2C come out with the water. And so I'm able to solve for this, and C is equal to 50. O2, I end up with 2 times 50 enter. 2 times A exit. 45 exit with HCHO. 2B exit with CO2. And C exits with the water. And I am able to solve that for A is 2.5. So I get exactly the same answers. So that's reassuring to me, okay? If I go through and use this to figure out percentages, since these are all based on 100 moles anyway, then I have 2.5% CH4, 2.5% O2, 45% HCHO, 2.5% CO2, and 50% water. What about selectivity? So selectivity is a ratio of how many moles of the desired product to undesired product are formed. So it's going to be 45 moles of HCHO formed divided by CO2, 2.5 moles of CO2 formed, which is 18. Now 18 is greater than 1, so this is a pretty good number. I consider 18 to be fairly large. I would be happy with this. Sure, larger would be better, but these are going to be good numbers. I think that this is a good reaction scheme. So in the next video, we're going to come back and we're going to look at another example of multiple reactions.